Hard to believe that we are already on Chapter 8, and Chapter 8 is dealing with rotational motion. Spent a lot of time doing that rotational graphics. I hope you guys like it. 8.1 is a very, very, very short section, so we're not even going to talk about 8.1. We're going to jump right into 8.2, which is talking about rotational dynamics. And when we talk about rotational dynamics, essentially we're talking about anything that's spinning. And when you really think about it, spinning or moving around a center point. So a wrench, all right, is rotating, even though it's connected to that. It's connected to the bolt. When it's moving, or nut, sorry, it's moving around in a circle, and that's rotating. So if we wanted to figure out kind of the distance of the lever arm, our first equation here is L is equal to R times sine of theta. All right, L is the lever arm. R is the distance from the axis of rotation and the force. And theta is our angle between the force and the radius. Now, a lot of times when you're doing problems in the book, if it doesn't mention a theta value, you can assume it's at 90 degrees. We have our bolt. And I'm going to do my best wrench impression here. That's awful, but all right. How am I going to turn that wrench? I'm really going to start by moving it sideways, and then it's going to go down. But then at that point, my wrench will be here. So if it doesn't give an angle, I'm always pulling at a 90-degree angle. And the sine of 90 degrees is 1. So you can kind of use that. So the lever arm is perpendicular distance from the distance. So perpendicular distance from the axis of rotation. So what do we mean by lever arm distance? Well, the lever arm distance is let's take away my second wrench drawing. All right, I have my wrench here. My lever arm distance would be this. All right. How long is my arm pulling down on the wrench? That would be my lever arm distance. So you can measure lever arm distance, the radius of the tool, or the angle at which you pull on it with that equation. The longer the lever arm, the easier the force. Right? Think about that. The longer the lever arm, the easier the force. Think about it in regards to doors. Why are all door handles on the outside of the door? Right? Because it's easier to push the door open when it's on the outside. Try pushing a door open on the inside next to the hinge. Right? It creates a lot more force than the outside of the door handle, and that has to do with lever, or the distance of the lever. Right? The lever distance is longer. Right? The lever distance is longer when the door handle's on the outside. Or if you're trying to get a nut, like a bolt or a nut off of something, the longer the wrench you use, the longer the wrench you use, the easier the force is going to be. The shorter the wrench, the longer the distance you have to apply. So that is lever arm distance. If we go down, we have to talk about torque. And torque is how effective that force is to cause rotation. Torque is abbreviated with a cool little letter. Kind of looks, if you draw it, looks like a capital T, all swag style. But torque is equal to force times radius times the sine of theta. Force times the lever arm, and our unit for this is a Newton meter. The theta has no really true unit. Radius is in meters, force is in newtons. You multiply them together, and torque is in a Newton meter. So, if we talk about an example here, a bolt on a car engine needs to be tightened with a torque of 35 Newton meters. You use a 35 centimeter long wrench and pull on the end of the wrench at an angle of 60 degrees from the perpendicular. How long is the lever arm, and how much force do you exert? Well, very, very, very first thing, let's break down what we have. We have torque is equal to 35. R. All right. R is 0.25. All right. And our theta is 60 degrees. All right. The very first thing that we are trying to solve for is our lever arm. What's the length of our lever arm? Well, lever arm, remember from the previous slide, is equal to R times the sine of theta. All right. Well, let's plug it in. 0.25. 0.25. Remember, it's in meters. times the sine of 60 degrees. And when we go ahead and do that, we end up getting point with sig figs, 0.22 meters. Next up, that was the first question. How long is the lever arm? Second one, how much force do you exert? Well, remember, torque is equal to force times R times the sine of theta. Well, if we go ahead and plug everything in, torque is 35 Newton meters is equal to force times R, 0.25 times the sine of 60. Do a little math, we get 35 is equal to F times 0.2165. We divide. We do that, our force equals 162, but we are confined to 2 sig figs, so our answer is 160 newtons. Okay. So that is how an example we would use lever arm and torque together. Now, finding net torque. We can use a lever and consider a lever as like a seesaw. All right. So on the picture we have two people. We have a very, very, very light, all right, light person on the top and a very, very heavy person on the bottom. And we want to figure out if that seesaw was to balance, where does the light person have to sit? Where does the heavy person have to sit? Now, obviously, the heavy person has to sit closer to the center of the seesaw, and the lighter person is going to have to sit farther away from the center of the seesaw. So how do we figure that out? Well, we can use this equation, net torque. And we know net torque from previous, torque is equal to the force of gravity really times the radius of the object. Well, if T1 minus T2 equals 0, we can take this equation and just set them equal to one another. So we can have Fg1 times R1 is equal to Fg2 R2. And this is for help stabilizing objects such as seesaws or any balancing equation when we're balancing. Maybe a tightrope walker walking across something would use this equation to figure out exactly what's the perfect balance that he could have. So here's our example. We're going old school. Mr. Kleinert, 120 kilograms, and Mr. Urbach, 75 kilograms, want to balance on a 1.7 meter long seesaw. Where should they place the pivot point? Where should they place the pivot point? So essentially we have two people of different weights. Ideally, if you had a seesaw, it would be in the middle, but that would mean that we both weighed the same, which we don't. So what we're going to have to do is we are going to have to shift. We're going to have to shift the center of the seesaw, right? We're going to have to figure out it's going to be shifted over, right? And how much are we going to have to shift it over? That's the equation we're going to have to use. Let's go through and analyze everything we have before we start. Mr. Kleinert's 120 kilograms. For this example, Mr. Kleinert is going to be person 2. Mr. Urbach is going to be person 1. So when we take the force of that, all right, remember, force of gravity is going to be the weight times 9.8. So Mr. Urbach is going to be 75 times 9.8. And when you do that, Mr. Urbach is 735 newtons. Secondly, when you do it for myself, force of gravity 2, for me, you're going to take 120 times 9.8, and you end up getting 1176. We're halfway there. Because if we use the equation Fg1R1 is equal to Fg2R2, we don't have either R. All that is told us, all that was given to us, is that the seesaw is 1.75 meters long. Well, what you could say, essentially, is if we look at our seesaw here, if I draw a seesaw, right, the whole thing's 1.75 meters long. R1's going to be here, R2 is going to be over here. We know they're going to be offset, which means that really we could say that our 1.75 is equal to R1 plus R2. Now, algebraically, I can go ahead and solve for R1. R1 is going to be equal to 1.75 minus R2. When I do this, I can plug in R1 for R2. And we'll show you how that works. If you have questions on that, we can talk about this in class tomorrow. I really want to get this idea of the whole plank's 1.75 meters long. That's equal to R2 plus R1. So how do we solve for R1? So if you have questions on that, let me know. So we're going to go ahead now, and we're going to plug in our numbers. FG1 is for Urbach. That's 735 times R1. Well, we know that R1 is equal to 1.75 minus R2, which is equal to Fg2, that's my force in newtons, 1176 times R2. Now you can see that we're going to solve for R2. We do a little distributive property action, and we get 1286.25 minus 735 R2 is equal to 1176 R2. R2 just adds as an X. So we're going to add 735 to each side. And what we're left with is 1286.25 is equal to 1911 R2. Our last step is to divide by 1911. And we figured out that R2 is equal to 0.67 meters. Which means that if I were to go on a seesaw with Mr. Urbach, what we would have here is the seesaw would be here. The center point would be right here. 0.67 is where the fulcrum would have to be away from me, and it would be away from Mr. Urbach 1.08 meters. Add those together, and you get 1.75 meters. As I mentioned earlier, if you have questions with this, particularly how I was able to algebraically, how I was able to rearrange this and plugging it up here, we will talk about it tomorrow in class. Other than that, have a great night. We'll see you tomorrow.